At a remote NASA research center in California's Mojave Desert, a team of pilots and engineers are preparing for what one pilot has called the most dangerous thing I've ever done. The experiment they are about to do could expand our ability to fly into space, but if something goes wrong, it could cost the lives of the airplane's 2 crew members. This is the ongoing adventure of flight research. Flying at the edges of the envelope, high power, high speed, high altitude, and high risk. The people who take on this challenge are a special breed. They're modern-day explorers, men and women who endure difficulties, setbacks, risk, and tragedy to fly into places no one has gone before. They are the seekers and adventurers who take us to the limit and beyond. Less than 100 miles north of Los Angeles lie the vast, windswept stretches of the Mojave Desert. For the past half-century, its parched, dry lake beds have allowed us to push flight to the edges of space. Today, NASA researchers are attempting to move spaceflight yet another step forward. The rocket engine they are testing on the back of this exotic Mach 3 spy plane is part of the X-33, an experimental aircraft designers hope will lead to a replacement for the space shuttle. The X-33 will demonstrate the technology required to build a full-scale reusable launch vehicle, or RLV. The hope is that these new technologies will reduce the cost of getting payloads into space.
Right now we use the space shuttle. Obviously, that is our primary launch vehicle. Putting that into orbit, it costs somewhere around, round numbers, $1 billion to launch a space shuttle. The desire is to reduce that by at least an order of magnitude to get into space. A single stage to orbit vehicle. In other words, with a space shuttle, we have the solid rocket boosters and the big liquid oxygen, hydrogen tank that are dropped off the vehicle as it stages into orbit. The RLV will go to orbit with no other assist other than its own engines.
But do we know enough to build this kind of vehicle? The X-33's job is to find out by flight testing technologies that a full-scale spacecraft would require. If successful, the X-33 could lead to a full-scale RLV that could replace the space shuttle, and early in the next century could be flying supply missions to the International Space Station. The development of the space station has also created a need for a second kind of space vehicle, one that could bring astronauts back to Earth safely in the event of an emergency. A prototype for this space station lifeboat is being tested at Dryden as well. The goal of the X-38 project is to develop the technology for a full-scale emergency crew return vehicle. In an emergency, astronauts could jettison the computer-driven craft and glide safely back to Earth. The X-33 and X-38 are the latest in spacecraft design, but in a sense, they are a step back to the future. Both vehicles owe their design to earlier research aircraft tested at Dryden more than 30 years ago. Known as lifting bodies, these stubby, wingless craft can withstand the searing heat of re-entry, but still generate enough lift to land like an airplane. Both the X-38 and the X-33 are lifting body designs, but the X-38 will be a glider. The X-33, on the other hand, has to generate enough power to get into space as well. That makes the most critical and untested part of the X-33's design the experimental rocket engine that will power it. The engine is called a linear aerospike. It's similar to other rocket engines with the exception of its nozzles. Standard rocket engines use bell-shaped exhaust nozzles that turn or gimbal to steer the rocket in one direction or another. The aerospike, on the other hand, uses the pressure of the atmosphere to serve as the outside edge of its two linear nozzles. This saves weight and structure and allows the aerospike to control a rocket's direction simply by increasing the thrust on one side or the other. The design has other advantages. As the rocket climbs, the reduced air pressure allows the aerospike's engine exhaust to spread out to match the requirements of its rapidly changing environment. This makes the aerospike engine an extremely efficient design that is also friendly to the environment.
It uses liquid oxygen and hydrogen. You burn those components and basically you get water, okay? The space shuttle uses solid rocket boosters that puts a lot of stuff in the atmosphere, a lot of aluminum compounds and that sort of thing into the atmosphere, which are not good for the atmosphere, obviously.
The aerospike engine has been tested on the ground, but the only way to know how or if the engine will work in the demanding environment of high-altitude, high-speed flight is for someone to take it there. This is the job of the test pilot.
It's a chance for me to do what I do best, which is to fly airplanes. And in a way, it's a silent challenge to say, okay, get out there, fly this airplane as precisely as you can, best you can, get the most data you can, satisfy the engineers, and do it all without any rehearsals. And I like doing these kind of things. And I like doing things that other people can't do. I'll never run as fast as sprinters. I'll never be a professional football player. But I can do this as well as anybody can do it. At least I think I can. And it's like a little test every day.
For the flight test, a 1/10 scale X-33 engine is being bolted onto the back of an SR-71 Blackbird.
It just so happens that the launch trajectory of the X-33, okay, beautifully matches the flight characteristics of the SR-71. So we can get data all along the trajectory path, up to and including the SR-71's highest altitude capability of around 80,000 feet.
Firing a rocket engine on top of such a demanding airplane will not be easy.
I think flying the aerospike is probably going to be the riskiest flight test I've ever done for a couple of reasons. We've got a lot of unknowns about the vehicle with this big experiment sitting on the back. And we're working with LOX and gas hydrogen. LOX is liquid oxygen. That's the the chemical that you mix with the hydrogen to make the rocket fire. And it's just a very explosive mixture. It's difficult to handle, and it's something that we don't normally do.
If you spill liquid oxygen onto the airplane that has fuel on it, you'll have a fire, because that's what happens when you mix liquid oxygen, which is obviously what makes things burn. So you can't have spills. Helium tanks are up close to 10,000, I think 8,800 pounds per square inch. These vessels themselves are potential bombs if they break. If it were to fracture, that's like a 20-millimeter cannon going off in the middle of this airplane. It's going to destroy the airplane.
Ed Schneider and Roger Smith know the risks. So do Bob Meyer and Marta Bonmeyer, the two flight engineers who will fly with them. Both Marta and Bob are competition aerobatic pilots in their own right and flight test engineers on the Aerospike project. When one is in the airplane, the other will be the mission controller for the flight. They feel the same pressure as everyone else on the team. But they carry one burden no one else does, because Bob and Marta are also married.
You know, knock on wood, I've never seen him have an accident, and he's never seen me have one, and if we do this right, neither one of us will have to have that experience. But no, I don't worry about that part of it. I just do not worry about that being an issue. I look at it as this is a job, and my job is to help them be successful today. And if it's in the cockpit, I'll do the best daggone job I can do in the cockpit. If it's in the control room, you bet I'll do the best job I can do there.
Because the risks are so high, the team decides to divide the flight tests into two parts. The first flights will determine if the SR-71 will even fly with the 14,000-pound Aerospike experiment on its back.
Flight research incorporates a lot of development. And involved in any development, a lot of patience is required, because systems, generally speaking, never work the first time the way you expect them to work.
Finally, almost 2.5 years after starting work on the project, the team is ready for flight.
Everybody, the morning of the flight, wanted this thing to be a success. Would have done it. I mean, they'd hand launch the airplane if that was going to get the airplane in the air, if that was an issue. I mean, I sat there in the control room, and you may even have tape of me sitting there watching it, you know, as, you can get off the ground, you can get off the ground, you know, it was important. And when I saw the wheels off the ground, then I said, okay, now get them in the wells, come on, get them in the wells, guys. Okay, and I said, now we have a flight.
In the weeks leading up to the hot fire flight tests, engineers and technicians comb every inch of the system for leaks and try to anticipate every possible problem. Still, there is no way to really predict the unknown.
I have to look at this from the standpoint that we have done the very best that we can do. Very best that we can do. Is the risk, the additional risk that's there, is that high enough that we should not try to do this? I have to convince myself that it isn't.
People would ask questions like, well, is it going to blow up? And you can explore that all day long and never come up with an adequate solution of how you're going to handle the danger aspect, the fear that I'm going to get hurt or my flying partner and I are going to get killed. You don't worry about that. You got a job to do. You're going to press on.
Ed Schneider and Roger Smith are not the first pilots at Dryden to accept high risks to push flight to the edge of space.
Flight research and experimental flight research is inherently risky business. Here at Edwards, there are many streets that are used every day by people coming to work, and they probably don't pay much attention to them. But virtually every name here is named after a test pilot who lost his life.
These wind-blown sentinels are silent reminders of the price men have paid to pave the road for the X-33, a road that began more than 40 years ago with a rocket plane called the X-15. The year is 1954. Frontline fighter planes are just barely going Mach 1 in level flight. Yet an idea is conceived for a plane that will go 6 times the speed of sound and fly into the edges of space. Even today, the hypersonic X-15 would be a challenge to build and fly. But in the late 50s, it was a task of staggering proportions. Its designers were trying to build a rocket plane that could fly twice as fast as a rifle bullet. It had to be controllable, not only in the Earth's atmosphere, but in the vacuum of space, where normal control surfaces would be useless. It had to be protected from the intense temperatures of hypersonic speed and re-entry. And it had to incorporate systems that could keep a pilot alive at altitudes where blood boils. But if it worked, it could open a door into a realm of flight men had only dreamed of before.
The entire purpose of advancing aerospace technology is to do new things, to go faster, higher, to provide new capability. In flight research and flight test, you have to go to the edge of the envelope. You can't sit comfortably in the middle of the envelope and learn.
To reach into the unknown and attempt something so difficult takes an extraordinary and dedicated group of people.
When you build an airplane like this, you count the divorces and the heart failures and the heart attacks on the thing. You know, I worked on the engineering design of that program for 3 years, and it was a night and day program. And for all of the people working on it, it gets to be a disease. It gets to be a tremendous drive, and the people on it are really fantastic people that build these kind of airplanes.
We were exploring the edge, the leading edge of something. At that time, there was nothing approaching it. You know, airliners were flying with piston-driven engines, and here we are out trying to go Mach number 6 and 7, and we were right at the edge, the leading edge of the technology, and people felt that and put their heart and souls into it.
The X-15 had to be built out of metal that could withstand 1,200-degree temperatures. An exotic nickel-steel alloy called Inconel X looked promising, but it had never been used outside a laboratory.
Inconel X was very, very hard to work with because it was a much, shall we say, denser material. It was much stronger material. Normal drills would just burn up on it.
The X-15 was also going to be powered by a new 600,000 horsepower rocket engine designed with a throttle to control its thrust. The engine, and the systems that powered it were both complex and dangerous.
Hydrogen peroxide that you have in your medicine cabinet is 3%. It's a bleach and a disinfectant. If you get high concentrations of it, and what we had was 98 to 100%, and if you just poured an ounce of it on a bush, in about 5 seconds that bush would burst into flames.
To fly the X-15 meant putting a pilot right next to those explosive chemicals in flight conditions no one had explored before.
I was always aware that there was risk with the X-15, but you couldn't dwell on that. If you thought of how risky it was, you wouldn't fly it, so you didn't think about how risky it was. But the apprehensions I had were of making a mistake.
But the high stakes in flight tests create strong bonds between pilots and their crews.
You get to know all of the mechanics and their wives' names and their kids and that, because then they begin working not only for their professional pride and their paycheck, but for their friend.
We are placing our lives in other people's hands, and they know that, and that's the beauty of the system. We say, you take care of us, we'll fly the airplane, and silently they promise we will take care of you.
At the beginning of the X-15 program, pilot Scott Crossfield was conducting a ground test of the new XLR-99 rocket engine when an ammonia tank overpressurized. The tank ruptured, and the X-15 exploded.
Just like being in the sun, just bright orange all around me. And then I saw just a black area or dark area coming, and it was an Air Force fire truck with just a wall of water just walking into this one. And down in the bottom of that wall of water was a guy named Art Simone. He was one of my mechanics, or our mechanics, North American mechanics. He was coming in to save my life.
Crossfield walked away from the accident without a scratch, and with his determination to fly the X-15 as strong as ever.
If I could find a pilot to fly the X-15 for nothing anytime, and I offered to fly it sitting on a tomato can if they'd give me the $5 million the escape system was going to cost. I had 3 explosions and a broken airplane on that, and I always got back in it.
The business of a test pilot is dangerous, no question about that. There are times when pilots don't come back, but test pilots wanted to fly airplanes, wanted to expand the envelope, wanted to be the fastest, the highest at the time, wanted to be the best in their business. And at this time, to fly the X-15 meant that you were the best in the business.
Flying the hypersonic rocket plane was a demanding and hazardous mission. To conserve its limited fuel, the X-15 was drop-launched from a B-52 at 45,000 feet.
When you reach up and hit that button and you're launched, it's just like you were sitting in a chair and somebody pulled a rug out from under you and you fell to the basement.
Got it. Launch. Turning on the lights, starting launch. Tank pressure is going up to 60.
The engine only burned for a minute and a half, but in that time accelerated the X-15 from less than Mach 1 to between Mach 5 and Mach 6. You had a lot of G's on your body, and things were happening at an enormous rate of speed, which causes stress when you have a lot of work to do in a short time to do it in. Milt Thompson said that the X-15 was the only airplane he ever flew where he was glad when the engine quit.
The pilots weren't the only ones busy during the X-15 flights.
We probably had involved 150 people at different range stations, at Air Force people associated with supporting us, the B-52 flight crews that had to be on board to support the vehicle, our crews on the ground here. Just getting ready, it took from about 1 o'clock in the morning right straight on to about 7:30. And people working pretty hard during that time period to get it done.
Each flight brought back new information and new problems that had to be solved.
That's what a research airplane is designed to do, is go discover the truth. And the truth can be what you expect, or it can be what you don't expect.
I don't think we really were surprised, anybody felt surprised that any of the problems occurred, we expected to see something. We just didn't know what they were going to be.
The information the pilots brought back from each flight let researchers improve the X-15 and added to their understanding about the unknown world at the edges of space. But those discoveries came at a price.
When an emergency happened, most of the burden of coping with it fell on the shoulders of the X-15 pilot. Pete Knight had an emergency one time where he lost his radio, and he was absolutely on his own from the minute the radio failure happened until he was successfully on the ground.
I was on an altitude flight, scheduled to go to 250,000 feet. And launch and engine light was normal, and I was in the climb, and at about 100,000 feet, the engine quit, and a few seconds later, I think every red light in the cockpit came on, and a few seconds later, everything went black. And so I couldn't see the instruments, but it didn't make any difference because most of those instruments weren't working anyway without any power. And so I'm still headed up. I'm climbing it at Mach 4 or something. And I've lost everything, and I can't control the airplane. And I haven't figured out, you know, whether I'm going to make it back or not yet. And so I'm looking down at Mona Lake and saying, you know, you better enjoy the view. It may be the last one.
Knight managed to regain control of the airplane and landed safely on a dry lake bed in Nevada. Not all the X-15 pilots were so lucky. Pilot Jack McKay had an engine problem that forced him to attempt a landing on one of the emergency lake beds. He jettisoned what fuel he could, but he was still heavy with fuel and going almost 300 miles an hour when he touched down. It was more than the X-15's landing gear could take. The X-15 flipped upside down, trapping McKay in the cockpit. McKay was seriously injured, but he recovered and made 22 more flights in the X-15 before leaving the program. The determined crew returned the crashed X-15 to the skies.
The morale always stayed high because we expected things to happen occasionally. I mean, accidents happen, and flight tests, accidents happen all the time. And so you took it in a realistic standpoint that, okay, it happened, now we got to go fix it, we got to go fly again.
The crew not only rebuilt the X-15, they modified it to make it even faster. In 1967, Pete Knight took it to a speed of Mach 6.7, a record that still stands. But only a month after that success, tragedy struck. Pilot Mike Adams was flying the X-15 at 230,000 feet when he apparently experienced some mechanical problems and possibly vertigo, which makes a pilot very disoriented. The X-15 began to turn off its correct heading, and Adams re-entered the Earth's atmosphere sideways, something the X-15 was never designed to do. The forces of re-entry sent the X-15 into a violent spin at 5 times the speed of sound.
I was a chase pilot on that flight, and I couldn't see any of it, but I could hear the soundtrack, and it's very terrifying. He knew he was in a high-altitude, high-speed spin, and so did the control room, but all of them were helpless to do anything about it.
You sit there and you wait for information to come in from people out in the field. You wait to get information as much as possible. You begin to think the worst, and you begin to think about the family and what you're going to do.
There wasn't anything I could do but listen, but it still was right on up there with the terror I've experienced in my career. I knew that wasn't going to have a happy ending, and it didn't.
At 62,000 feet and 2,592 miles an hour, the X-15 finally broke apart. Mike Adams was killed.
It's something you work to never let happen, but you always know in the back of your mind that perfection is something that's not going to be achieved in this process. That is part of the process. There is inherent risk. There's a real human investment in flight research, and it's certainly blood involved. People have sacrificed over the years for the sake of moving technology forward. They do it for the belief that it's important for the country. They do it because they are patriotic. They do it because it's for their kids and their kids' kids, that it's going to make a difference in the future.
Over the course of 9 years and 199 flights, the X-15 laid the groundwork for every space exploration program that has followed.
I don't think there's ever been an experimental test program in the history that has come close to being as successful or providing as much information to the industry as the X-15 program, from stability and control to heating, to physiological data, to structural data, to just any discipline you want to talk about. The X-15 had an input to it.
It built confidence in our ability to engineer anything we could write the requirements for. And it's that kind of respect for your engineering that allows us to go to the moon in Apollo without ever testing the thing.
The X-15 had carried with it tremendous technological risk. But everything that we do hypersonically goes back to X-15 data. Why? Because it's the only hypersonic data, flight data, that we have.
The X-15 was the first step on the road to a reusable launch vehicle like the X-33. But the X-33 also owes its heritage and its unique shape to another high-risk flight program from the 1960s. Even as the X-15 was preparing for its first flight, officials at NASA made the decision to pursue a simpler ballistic capsule design for the first Mercury spacecraft instead of a more sophisticated flight vehicle. It was a disappointing decision for the pilots and engineers at the Flight Research Center, who wanted NASA to develop a spacecraft able to fly back to an Earth landing. The concept they championed was an unusual, wingless vehicle called a lifting body because it got enough lift to fly solely from the shape of its fuselage. But a lifting body had never been flown, and NASA headquarters was not interested in pursuing the concept. Undaunted, an engineer named Dale Reed built a small radio-controlled model of a lifting body and flew it at a ranch near his house. His wife filmed the flights lying on the ground to make the model look more realistic. Armed with the film, Reed and several others convinced their boss at the Flight Research Center to let them build a lightweight, full-scale version of the model, without headquarters knowledge or approval.
Because of the extreme lack of confidence in the lifting bodies, we felt we would propose this as strictly as a wind tunnel model. But on the side, talking to my boss, he said, well, now if you just happen to build it so it can fly later, that's okay.
Well, the people that got into a lot of these programs were very innovative people that were very thinking way into the future and very imaginative people, and were not afraid to try something new.
The team set up shop in the corner of a hangar and got to work. But without headquarters approval, funding was sparse.
We had to design and build this in a very low-cost fashion. Had to use what we had here. Well, it turns out that we had experienced home builders, engineers and technicians that had built several home-built airplanes. We called on our resources right here in Antelope Valley.
A lot of times people work weekends and do a lot of things on their own, so nobody watched the clock.
The crew built the frame out of steel tubing and covered it with a plywood shell. The whole project cost about $30,000. The crew didn't actually have permission to fly the plane, which they dubbed the M2F1, but their boss, Paul Bickle, agreed to let them tow it across the dry lake bed as long as it stayed on the ground.
It turns out that we had another piece of talent within the organization. Name was Whitey Whiteside, and he was a hot rodder, a car racer. And so we put him to work of putting together a special tow vehicle.
I pretty well had a free hand in making that Pontiac be a powerful, go-fast son of a gun.
Armed with a car powerful enough to tow the M2F1 almost 100 miles an hour, the team was ready for more than just a ground tow.
In our engineering calculations, we had figured out that the exact liftoff speed of this vehicle would be 82 miles per hour. And so we felt that if we just sort of slipped up to this 82 miles per hour, we might get it just, pretty light on the wheels. Well, Milt sort of accidentally took it up to about 85 miles an hour. Oops, we were flying all of a sudden.
The sight of a car full of engineers barreling across the lake bed with a tubby plywood ship in tow may have looked more like a fraternity stunt than a serious research project. But the unauthorized flight test proved that the lifting body, nicknamed the flying bathtub because of its stubby shape, would fly. Having taken the concept that far, the M2F1 crew pushed for permission to take the plane aloft to test its ability to glide back to a safe landing. Even at the Flight Research Center, some people felt that it was too high a risk to take.
It's always a challenge because in the case of experimental aircraft, you're always pushing the frontier. You're always pushing the edge. And so it's crucial to know how big of a bite to take. Now, if you're too reckless and fly before you have enough data, then you may be, in fact, taking too high of a risk. If you're too conservative, you'll never fly. And that's perhaps the safest approach. But we're not here to only keep airplanes locked in the hangar. We're here to fly.
In the end, Bickle agreed to let the team fly the M2. But as pilot Milt Thompson took off on the plane's first flight, everyone held their breaths.
I think technically a person believes they're ready. But I don't know anybody in this business who hasn't stood on the sidelines or in a control room or out on the runway and watched the first flight that hasn't had some apprehension and held their breath because, again, of the unknown. And we know over the years that unknown factors have led to mishaps.
The M2F1 didn't fly like any other airplane NASA had tested, adding tension to the flight.
It looked like it was a bomb heading towards the ground. It was diving towards the ground, and it did not look like an airplane because the lifting bodies, even though they do create lift, are very inefficient compared with airplanes. We didn't really breathe until it came level and touched down softly on the lake bed.
The team had proven that the M2 shape could fly. Their success led NASA headquarters to approve an expanded flight test program with heavier, powered lifting body designs. But the early lifting bodies were very difficult to fly.
Well, we were instrumented physiologically, and I think heart rate's 180 degrees, 180 beats per minute is not unusual. So that means you're working very, very hard, and your body is really putting out its utmost.
The M2F2 design had a bad tendency to oscillate or roll side to side that would eventually have terrifying consequences.
That first version was very difficult to fly by all the pilots, and we knew it was very marginal.
For pilot Bruce Peterson, the margin would prove a little too narrow. Coming in for a landing on his third flight in the M2F2, it began to go out of control.
You could see that Bruce had a problem when you could see the vehicle rolling back and forth before the landing.
And when I did recover, then I was at low altitude and had been forced off the main runway heading. Also, I had a helicopter in my way. So I tried to get underneath the helicopter or behind the helicopter, and either I got caught in his rotor wash or I misjudged my altitude, but when I put the gear down, one gear door caught on the lake bed, and that flipped the vehicle. So I ended up cartwheeling down the runway. Last thing I remember is a glass from the nose window coming at me, and that's the last I remember.
The whole operation occurred almost instantaneous. You're sitting there, you expect him to pull landing gear, and he does get it out, and then you see him touch down, and then you see the roll starting. You don't have time to react. I mean, the emotions don't even come to you until after the fact, until after the airplane stops, and you have this sad feeling in your heart that you're going out and pick a fellow friend up off the lake bed, and that was my feeling. I was going out and pick somebody up that I cared about, knew about as an engineer and as a pilot over quite a few years, and I didn't look forward to going out there with the crew to the airplane.
The footage of that crash was so dramatic that it was used for the opening sequence of the television show The $6 Million Man. But although Peterson was badly injured and would end up losing an eye from the crash, he survived.
But when I got out there, everything changed. The airplane be damned, the pilot was okay. We'll worry about fixing the airplane later on. And that's what we did.
NASA headquarters didn't want to rebuild the crashed vehicle, so McTeague's crew instead finagled permission and a small amount of money to inspect the damaged airplane, quietly fixing each damaged part as they inspected it.
We were all technical people that knew what had to be done to prove the lifting body concept. And this motivation kept us moving, bridged us across the, you might say, the political barriers that say, hey, you can't do this, hold up.
The effort took 3 years, but the rebuilt M2, modified to eliminate the dangerous oscillation problem, returned to the skies and completed another 27 flights before the program ended. Eventually, the lifting bodies flew to over 90,000 feet and proved that a spacecraft with minimal gliding ability could still be controlled and brought back to a safe landing without engines. As a result, the space shuttle was built without landing engines, allowing it a much greater payload capacity. Those early research flights also proved that the highly efficient lifting body shape could be controlled and landed safely. The efficient lifting body shape, as well as the more efficient linear aerospike engine, is what makes the idea of a single-stage-to-orbit spacecraft possible. But those pioneering discoveries took an extraordinary amount of work and effort. They also cost Mike Adams his life and Bruce Peterson his research flying career.
Do I have any regrets about flying? I love flying, and you do that kind of work, you take your chances. In this business of research flying, there's certain dangers that go along with the territory, and when you get hurt or get killed, obviously it's very difficult for your family. And if I didn't think it was worth it, I wouldn't have gone into that line of work.
In the world of flight research and experimental flight, the cost is really blood, sweat, and tears to reach the goal, to fly an airplane for the first time. It's built on the work, the failures, the tears, the successes, in fact, the personal sacrifice of hundreds of people, all for the purpose of benefiting a larger group of people.
The effort and sacrifices of Dryden's lifting body pilots and crews laid the groundwork for the X-38, a vehicle that might save the lives of future astronauts.
There are 2 lifting body designs that are actually going into space. Both designs rely on the data that we produced 30 years ago.
One of these is this stubby prototype, the X-38. It's designed to be a crew return vehicle, or CRV.
The X-38, which is the lifeboat to be attached to the space station, assured crew return vehicle that can be maneuvered, because it is a lifting body, it can be flown like an airplane to almost any spot on the globe.
Its onboard computers, using the Global Positioning Navigation System, will aim it to a pre-selected landing site. At about 20,000 feet, a series of parachutes will deploy, slowing the descent. The final parachute, a large rectangular parafoil, will glide the craft to a slow and smooth touchdown. Atmospheric drop tests of a 1/6 scale model have been successful.
There. Beautiful. And the right skid touch first, you can see here. And then left skid, right skid.
After more than a dozen tests, the concept is working as planned. The X-38 model has good control characteristics, and the parafoil is very effective in guiding the vehicle to a soft landing. Tests of a nearly full-scale prototype of the X-38 are underway with the aircraft attached to Dryden's B-52 mothership, the same aircraft that dropped the X-15 and the lifting bodies in the 1960s.
Launch. Good hatch. Good job. Good reposition. Looks good. Zero stage, looks good. Let's slow down now. First stage. That's the second stage. There's third stage. Okay, Mike, we are real close now to the IP. Low key, we're real close. You think a little? You bet, Stan, yeah. Altitude 9.5. Chase helo. Touchdown, the vehicle's down. The vehicle is down.
In the future, a modified X-38 prototype will be launched in orbit by the space shuttle and tested to automatically land back on Earth. If all goes well, as many as 8 CRV vehicles will be built to serve the International Space Station.
In this case, it, like I say, it took 30 years after we'd done all this work, but it makes it feel that you did the right thing and you believed in the concept at the time, and we pursued it at the time.
It's been a long road from Dale Reed's lifting body model flights to flying the X-33 and X-38 prototypes. Each step has taken the courage of people willing to risk failure and venture into the unforgiving realm of the unknown. It's a legacy that is never very far from the minds of Dryden's research pilots, especially as they prepare for the high-risk SR-71 laser tests.
When you get ready to go fly the SR-71, there's about a half an hour required to get in the pressure suit and do pre-breathing and test out the systems and everything. And then there's a period of time when you're sitting there in the suit waiting to be driven out to the airplane and get in the airplane, and there's always usually 5 to 10 minutes of quiet time. Two thoughts come to me. The first thought is the hopes and dreams of a whole lot of people are now riding with me. They've done everything I can, now it's my turn, and no one else can do this. Just me or me and my flying partner if it's a two-person airplane, my flight test engineer in the case of the SR. The other thing that occurs is on a program like the Aerospike, when you're expanding the envelope and flying the airplane for the very first time, you are doing something no one else has ever done. You are pushing back the frontiers of science every time you go do this. You may only be pushing them back a little bit, but you are pushing them back. And that goes all the way back to the Wright brothers. So from now to then, there's a connection. And it's really a neat feeling.
Every system, every connection, every contingency plan has been carefully checked. But this is the moment of truth.
This is where you find out whether a concept really works, whether you've thought of everything, whether there are unknown factors that may alter the performance or change your ideas. Flight is reality. Everything else is fantasy.
The crew knows the risks, and they're ready to face them.
I don't feel very happy about going up with oxygen and hydrogen on my back, but on the other hand, I feel very confident that the team that we have here, the people that we work with every day, they are never going to ask us to go fly that airplane until they feel absolutely confident that it's going to work. And I trust that. When they say, our people here When they say, we think it's ready to fly, then I believe it's ready to fly.
I love that airplane. I love the SR a great deal. It's one of my, when I think about it, it always brings a smile to my face. And I love to share it with people. And if I can make it show better by being in the airplane or being in the control room, I'm going to be right there. There was a special passion for the airplane. There's also, it's even better when you can do something no one's ever done with the airplane and actually advance the state of technology. I just cannot waste any more energy on being worried about it. Let's just do it right.
Ed and Bob strap into the SR-71 cockpit. Ground crew check their equipment and give them a final briefing. Pilots climb into F-18 chase planes. Their job is to check the SR-71 in the air and offer advice if necessary. But they know there is little they can do if something goes wrong. Ed Schneider and the other SR-71 crew members are the latest in a long line of proud professionals who have risked their lives to prove an idea possible. The passion that drives them is the same one that drove the X-15 and lifting body pilots, and every explorer since the beginning of time. We've traded sailing ships for rocket ships, and oceans for air and space, but the effort is the same. No matter how far technology advances, the only way to know what lies beyond a new horizon is for someone to go there. It's an effort that requires courage, dedication, and sacrifice. But the explorers who take on this challenge have expanded the horizons of our world and made what was once impossible, possible. It's a continuing adventure, not only about flight, but about the human spirit. As long as we wonder and as long as we dream, that spirit will continue to take us to the limit and beyond.